temperature coefficient of resistance. Actually, this is the change in temperature per unit original resistance per unit change in temperature. Usually this original resistance is taken at a temperature of 0 degrees centigrade. So the resistance per unit change in temperature, so it's the change in temperature per unit original resistance per unit change in temperature. So the expression is given by, this is the change in temperature they are referring to, the qualitative part, the quantitative part. Now this is the change in temperature they are referring to, and this is the original resistance they mean, and this is the change in temperature they are saying up. So if, suppose, as I said, original resistance they usually consider at 0 degrees centigrade. So for all the cases whereby the initial resistance R theta 1 at the beginning of experiment is equal to the original resistance, when R0 is equal to R1, such conditions whereby the theta 1 was also the temperature 0 degrees centigrade, that means this is also equal to this, and it can be changed. You can replace that by R0. Doing so, you can therefore simplify this equation. When you take that there, you can see that is alpha times R0 times theta, whereby the theta 1 we have said is 0 degrees centigrade, then plus R0, because finally this R0 will be brought this side to be plus added. So resistance at temperature 2 will be equal to that. So you can factor out R0 and remain with one, a simpler form. So in general, the ratio of resistance at theta 1 resistance theta 2 is equal to that much. Examples where such can be applied is that, for example, the winding of a motor has a resistance of 80 ohms at 15 degrees centigrade. Find the resistance at 50 degrees centigrade. So the temperature coefficient of resistance given is 0.04 per degree centigrade. So solution, we have our formula that resistance at temperature 2, as you can recall, resistance at temperature 2 is equal to resistance initial plus times 1 plus alpha times resistance 2. So we can solve an example here, that the winding of a motor has a resistance of 80 ohms at 15 degrees centigrade. Find its resistance at 50 degrees centigrade. The temperature coefficient of resistance is 0.004 per degrees centigrade. There are two approaches that you can use here. I want you to note that this is the general equation, but we use this equation only when we are referring to the initial temperature theta 1 as 0 degrees centigrade. As such, that's the only case where R theta 1 can be equal to R theta 0. So this equation is only valid when the initial temperature is theta degrees centigrade. Therefore, even the resistance at theta 1 is resistance at 0 degrees centigrade. So there are two approaches of solving this question. So I'm going to write the first approach here and the second approach here. The good thing in that in all the approaches you are first required to find the R0, because in the equation that we are given temperature coefficient of resistance, we are given resistance, we are looking for this resistance, we are given this value, and we are given this value, but we are not given these two values. Remember, as I said, if you have two unknowns in an equation, you will always solve the question with two equations. So here we have one equation, so we are supposed to generate another equation that can help us eliminate one unknown and remain with the other unknown. Therefore, as he has done here, is first you are required to, because this is what we are looking for, the alternative we should find is to try to find the value of R0, and we will find the value of R0 using this equation, and we will use this equation only when theta 1 is equal to 0 degrees centigrade. Therefore, we will use this first statement to solve for r theta. That we will assume that theta 1 is equal to 0 and theta 2 is equal to 15. I said there are two approaches of solving, but this is the general way of finding r naught. I'm doing this so that we can be able to use this value, because our initial has to be 0 degrees centigrade. Therefore, if we use this formula, our r naught, we can get it, because r at 15 we have, it is 80 ohms, divided by 1 plus 15, which is the theta 2, times temperature coefficient of resistance, and we can get our r naught there. So from here we have two approaches. We can proceed with this formula, but this time assuming that our theta 1 is 0. Remember, whenever we have to use this formula, your initial theta 1 has to be 0 degrees, otherwise you use the other formula, this one. So for the first way, from here, when we want to solve now the second part of the question, we have one approach that we can assume theta 1 is 0 degrees centigrade, and we can assume theta 2 is now the one that we are asked at 50 degrees centigrade. Therefore, in our equation, here comes in r 50, r naught plus 1 times temperature 50. So simply from here we can just solve that resistance at 50 is equal to r naught 75.47 plus 1 times 1 plus alpha, which is 0.05, and we can get the answer. Similarly, from here another way can be using our way that alpha is equal to r1 minus r2 divided by r naught theta 2 minus theta 1. Okay, so we want to solve for, this is r2, this is r1. So since we are done with the first part, if we want to use this formula, then we can assume that r1 is 15, r1 is 15 at 15, and r2 is at 50. Okay, and we have r naught there. So theta 2 we know that is at 50, and theta 1 is at 15. Then we have this, so we can solve for this simply, that if you want to make this the subject, you get r at 50 now is equal to alpha r naught times theta 2 minus theta 1, then this plus resistance at the second temperature, at the first temperature. Okay, at the first temperature, this time we took is 15, so you can put 0.04, you can put r naught, the one which you have calculated. Theta 2 for this case is 50, and theta 1 for this case is 15. R at 1, where the first temperature is 15, is 80. So solving for that, you'll get the same answer. A second example is that we have a conductor having cross-section area of 15 centimeters squared and a specific resistance of 7.6 ohm micro ohm centimeter at 0 degrees centigrade. If the temperature coefficient of resistance of material is 0.005 per centigrade, estimate the resistance in ohm per 2 kilometers when its temperature is 50 degrees centigrade. Estimate its resistance in ohm per kilometer when its temperature is 50 degrees centigrade. So we are given the area 15 centimeters squared, we convert it into SI units, and the resistivity as micro ohm centimeter, we convert it into the units, and of the length, as we are told, we should estimate 2 kilometer. So we consider our length as having 2 kilometers, which is 2000 meters, and we have temperature coefficient of resistance as 0.005 per centigrade. So we are asked to find the resistance at 50, resistance in ohm per 2 kilometers when its resistance is 15. That means when the conductor is of length 2 kilometers and at resistance of 50, we should find the resistance. So we know that at 0 degrees centigrade, the resistance 0 degrees centigrade is equal to the resistivity at 0. You see, when the resistance is affected, even the resistivity changes by the temperature. That's why we have resistivity at, we have to specify resistivity at what temperature. So we have resistance at 0 degrees centigrade, resistivity at 0 degrees centigrade, and we have length divided by the area. This is equal to the resistance. So the resistance at 0 degrees centigrade is equal to the resistivity at 0 degrees centigrade, which is 7.6 times 10 power negative 8 ohm meter, times length, which is 2000 meters, divided by the cross-sectional area that we are given, and we get the resistance is 0.101. It means for these 2 kilometers, for a resistor at 0 degrees centigrade, for conductor at 0 degrees centigrade, to have resistance of 0.101. But for resistance at 50 degrees centigrade, remember I said when we use this formula, we assume that our initial temperature was theta 0 degrees centigrade. Good enough that we have only two temperatures and one of them is 0 degrees centigrade, so we can proceed with our formula that this is the resistance at 0 degrees centigrade, which is the one that we have here, and alpha we are given, and this is the temperature, the new temperature we are looking for. So 0.101, you put in the numbers and you get your resistance at 2 kilometers when its temperature is 50 degrees centigrade. The essence of giving you 2 kilometers is to help you to use this resistivity, and this cross-sectional area to find the resistance at 0 degrees centigrade. So from there you can proceed with normal answers.